Good morning, ladies and gentlemen, and welcome to a super exciting webinar. This is the first ever South African hosted IDEA StatiCa webinar, and it serves as an introduction. So if you've been following some of our news, you would have seen that IDEA StatiCa actually went live in South Africa for the first time just over a month ago. And this just serves as an introduction for all of you as to what you can expect from the IDEA StatiCa suite. So without further ado, let's jump straight into it. So our agenda for today will consist of an introduction of those present. We've got some exciting guests in with us today. An overview of IDEA StatiCa. We look at some key modules and capabilities. So that will consist of 2 modules out of the full suite, which will be steel connection, and then we'll have a CB FIM discussion regarding that. We'll look at concrete detail. Then we'll look at a live demonstration of steel connection. So we'll cover a very basic workflow, and then I'll also show you quite a complex connection just to show you what the workflow is like, and also then what is capable within IDEA StatiCa steel connection, which is really at this stage their claim to fame, but it won't stop there. We know that they're working on some very, very exciting stuff that will be released in the future. Then we'll have a short section on integration with other software. So what does IDEA StatiCa support in terms of integration? And then, of course, we'll end off with a conclusion, which will consist of a Q&A in a sense. But there is a live chat going. And if you have any questions, please pop them in the live chat throughout the webinar as you sort of think of something to ask. And then we'll definitely make time to answer those questions. There is a very short, or there's a small latency between the feed and then what you see. So we really do encourage you to, if you have questions, please pop them in the chat and we'll be sure to get to them throughout the presentation or cover all of them during our conclusion. All right, so as an introduction, first and foremost, it's myself, Jacobus Oberholster. I'm an AEC and Procon technical consultant for micrographics, and then I will also be part of the South African IDEA StatiCa technical support team, and I'll be running through the most of today's webinar. With us, we've got Dominic Barrick. He is an IDEA StatiCa product engineer, and he'll be running with the CB FIM discussion for us. And we've got Audrey Hudek, who's also an IDEA StatiCa product engineer, and he'll be running through concrete detail with us. So I do apologize if I got their names wrong, but for the most part, they'll know exactly who you're talking to if you have a question. And if you feel like addressing a question specifically to any one of the presenters, you are more than welcome to do so. So, all right, let's just look at a quick overview of IDEA StatiCa. We have got IDEA StatiCa at the top, which is, of course, the product. And within that product, we've got 3 tabs or wings, which consist of steel, concrete, and then the BIM link, which is also known as checkpot. Now, within steel, we've got connection and member, and then connection will receive quite a lot of attention from us today, just because I find that it is absolutely revolutionary for what it can do and how easy it is to work with. Then we've got concrete, and within concrete, we've got RCS, we've got detail, we've got member, and we've got beam. And then Andres will be looking at the detail aspect of the concrete modules. And then right at the end, we'll cover a little bit on the BIM wing. Well, all right, let's go straight into our steel connection. Now, for those of you that are familiar with steel structure design in the South African context, or actually, well, probably globally, we know that connections often govern a design, and these can take the longest. For us in South Africa, we've got multiple resources available. We've got the SAISC Red Book, the SAISC Green Book, and then we've got multiple software packages to assist as well. But all 3 of these resources are limited in terms of the level of complexity that can be designed. And complex connections that are becoming more prevalent actually because they allow us to save on materials, and also just the number of members we have in a structure. As an example, there are a lot of reasons why we would go complex connections, or even that we're looking at crossing larger spans with smaller elements, whatever it might be. Complex connections are definitely becoming more prevalent within the engineering context. And these complex connections are hard or even impossible to design by hand. So what do we usually do when we're faced with a complex connection? Well, we over-design um, a lot, right? So we over-design a lot. We take our ULS factors and we multiply those even more. I've even come across scenarios where people use a factor of 5 when it comes to complex connections or complex structures. And the reality is that this has a serious knock-on effect, because not only does that member become excessively more expensive to manufacture, your members are also larger as a result. So if you can think of, let's say, a complex orange connection with multiple stiffeners, etc., and multiple connections coming in at that point, if you enlarge your connection, then your rafter also has to get bigger, or if you overestimate the forces that you will have acting on that joint, then your connecting members will also be affected. And then, of course, steel isn't cheap either. You guys remember the 2021 price increases? We had price increases of 91% or even more in some contexts. I remember the price of steel increasing significantly by a factor of 2 just over a month. And that had some serious effects on our projects. I remember being a project manager at that stage, and it was utterly terrible, right? What a contractual nightmare to deal with. And it has been an upwards trend from there. Of course, the increases haven't been as hectic as they were back in that stage, but we still see that the price of steel is increasing and will continue to increase. Actually, we're not in a world where the amount of raw materials that we need is just available, or it's unending. It's actually a finite number of resources. I just see in the chat there, Johan Duplessis, I think my internet connection is bad. I just want to see if anybody else is present, if you guys are experiencing the same thing. If anybody else can say, do you find that the feed is a bit laggy, or are you okay? If we can just have another comment in the chat there, just to make sure that it's not a problem from our side. Okay, no issues. See there from Pinar. Okay, thanks. Oh, Johan, sorry, man. I think then the problem is with your internet. Okay, so no issues. All right. Okay, thank you for those that did comment. Johan, at least the recording will be available afterwards, so you are welcome to actually just refresh your experience afterwards. But yeah, do keep us posted if there's a particular topic you'd actually like us to cover again. If we have enough time, then we'll definitely look at those topics again. But all right, so just back to where we were. Steel is only going to get more expensive. And in the days we are in, considering environmentally sustainable approaches to design, which actually should start even at the design stage, optimization is not just a nice to have anymore. It is essential. And that is where IDEA StatiCa comes in, especially when we think of the connection module. You can see actually the 3 connections on screen are actually from within the software itself. These are not just, those, you think of what you're seeing now might not represent a true product kind of thing. This is something that you see that you can actually create within IDEA StatiCa steel connections. So from the most simplest connections to the most complex ones, IDEA StatiCa will help you to actually analyze and design and optimize your material use, which is epic. And they're only adding more to the features where it comes to, I think there are some detailing features for the future. You can export your connection as an IFC and even as a DXF, and actually details or puts all of your plates. Okay, good. I see from Jan. All good now. Great. It actually puts all of your plates in a DXF and allows you to detail them from there, which is really very cool. Now, over and above this, there is a massive online library with over 10,000 pre-designed connections, but over 700,000 variations within those pre-designed connections. And I think it's only growing. I mean, Dominic is welcome to add to that if he wants to, once it's his opportunity to do so. But the nice thing here is that even if you're fresh in the use of the software, you can actually go to this online library that is available for free for anybody, and you can select a particular connection that best suits the one that you are looking at designing, and you can import that into IDEA StatiCa connection, and you can work with that as a template. I've actually used it to look at what are the sort of operations that we use to develop or to model a specific type of connection, which is really very cool. So even if you don't have access to IDEA Static at the moment, you can actually go and look at this online library and see what's available there for you as a user. And I think you can even open up the connection, look at it there, and I think it's not just the viewer. You can actually work with the connection in some sense, but I'll ask Dominic just to expand a bit on that in terms of what the functionality is with the online library. But that is really very cool. So it even helps you with a bit of creativity. If you're looking at designing or modeling a type of connection, you're not exactly sure how you're going to approach it. The online library is there to help you. Also, you don't need to use the online library. You can actually just design a connection from scratch, and we will look at that closer to the end of our webinar. So right now we're getting to quite an exciting little bit. We are going into our CBFIM section. So it's component-based finite element method. And this is the analysis philosophy within IDEA Statica connection. This is how it is possible for you to actually analyze such complex connections. So I'm going to hand over to Dominic, and he is going to run with this portion of our webinar for today. So Dominic, over to you. I can hear you. I just want to check. I can see your screen on my side and it is visible in the chat. Can those that are viewing in, can you just confirm whether you can hear him? Yeah, just hold on there, Dominic. I'm just going to check something. Can you just say something?
Something.
Okay, there we go. Thanks for saying something. Okay, I think they said initially, the attendees said they can't hear you. Can we just confirm again if you can hear Dominic? So Dominic, you just can introduce yourself quickly.
Right.
Okay, there
My
we
name
go.
is Dominic.
There you go. Okay, Dominic, the floor is yours. Sorry, man.
All right, thank you. Hello, everybody. My name is Dominic Baric. I work as a product engineer here in IDEA Statica in the headquarters that are based in Brno, Czech Republic, heart of Europe, basically. Today I would like to talk about the component-based finite element method and the model itself. CBFEM, as we call it, is what is behind IDEA Statica connection. CBFEM is a synergy of the component method and finite element analysis. CBFEM method is based on the idea that most of the verified and very useful parts of the component method should be kept. However, the weak point of the component method was replaced by modeling and analysis using the finite element method. What it really is, it is a unique method for design and co-checking steel connections, members, and anchoring. It can be used for the majority of joints, anchoring, and details of various topologies. The CBFEM method provides clear information about the behavior of the joint or member. The method is quick, efficient, compliant with the code, and it is a design-oriented finite element analysis optimized to deliver results relevant for code check, and at the same time, it covers real structure behavior. Basically, it is a method developed for the structural engineers by another engineers. All of the modeling is performed by manufacturing operations such as plates, bolts, anchors, pins, welds, and cuts. Basically, imagine you doing, as you work in some kind of a CAD software, and you really use the operations that you would use normally. And then the whole model, the FEA model, is generated automatically and divided into individual plates that are meshed with the shell elements. Bolts and anchors are represented by special nonlinear springs, and welds are discretized and modeled as a special constraints, enabling the stress redistribution due to their plastification. Thanks to that, forces are calculated without simplifying presumptions. The interaction of components is calculated as well. Moreover, the results include prying forces because of the consideration of the real stiffness of the components. Strength analysis is the most important analysis of the joints, and straight check of plates together with co-checks and components are performed by elastic plastic analysis. The analysis of joints is materially nonlinear, and the load increments are applied gradually, and the state of stress is searched for. There is also a geometrically and materially nonlinear analysis available by default for hollow sections, which require that. Here in this slide, you can see the diagram, the graph that basically describes it is safe and you could say even conservative design, but the one that is according to the code. Right, now I would like to talk about a little bit about the model, which you can see each plate is meshed automatically and individually. There's no intersection of plates, and you can see it investigated in the model. The elastoplastic model of welds gives real values of stress, and there is no need to average or interpolate the stress. Calculated values at the most stressed weld element are used directly for co-checks and of the weld component. This way, there is no need to reduce the resistance of multi-oriented welds to unstiffened flanges or long welds. This is a visual representation of the weld in the model. A special elastoplastic element is added between the plates. The element respects the weld throw thickness, position, and orientation. The equivalent weld solid is inserted with the corresponding weld dimensions. The nonlinear material is applied, and elastoplastic behavior in equivalent weld solid is determined. Excuse me. Coming to bolts, in the component based finite element method, the bolt with its behavior in tension, shear, and bearing is the component described by the dependent nonlinear springs. Bolt assembly consists of bolt, washer, and nut, and is simulated by nonlinear spring, rigid body elements, and gap elements. More on the topic could be found on our website in our theoretical background. And CBFEM. In CBFEM, it is convenient to simplify the concrete block as a 2D contact element. The connection between the concrete and the base plate resists in compression only, and compression is transferred via the Winkler-Pasternak subsoil model representing the deformation of the concrete block. And what does it give you exactly, this CBFEM in the connection application? Well, you receive a check of plates. You receive equivalent stresses according to von Mises and plastic strains. The plates are modeled with elastic plastic material with nominal yielding plateau to slope according to the Eurocode. And the material behavior is based on the von Mises yield criterion, and it is assumed to be elastic before reaching the design yield strength. You can see that all of the plates are modeled as shell elements. The ultimate limit criterion for regions that are not to buckle is reaching the limiting value of the principal membrane strain. 5% is recommended to the Eurocode, and that is exactly the value that is critical in the CBFEM and our application as well. Then bolts in IDEA StatiCa are checked according to corresponding standards. you can see in this slide that you're basically given all of the code checks performed in the application by itself automatically and are corresponding to the code. And same applies for welds in IDEA StatiCa connection. You can see the same, and you would receive the same thing for anchors as well. While this method is not just, it wasn't done in a garage and set free onto the market. It was created and developed in cooperation with two universities from Czech Republic. Two of these universities have dedicated teams to spend over 3 years on verification and validation of this method that has been invented mostly by Professor František Wald. And these universities have verified and validated all of the results. And then they were further validated and verified by some other universities in the United States. It would be the University of Tennessee, Ohio State University, and the University of Illinois at Chicago. Just furthermore, I would like to talk about some other analysis that you could find in the connection that are based on the CBFEM model. You could perform a buckling analysis to identify global buckling modes and local buckling of plates, and as well as perform a stiffness analysis, which helps you to classify your connection as rigid, semi-rigid, or pinned. And you are provided also with a moment rotation curve diagram, code stiffness limits, and the initial stiffness and second stiffness. And you can calculate stiffness of torsional and torsional stiffness as well. All of these can be found in IDEA StatiCa connection. And just some real life, well, just the examples what you could do within this is you can get really complicated. There aren't many limitations to what can CBFEM can do, but of course it doesn't have to be just that complicated. You can perform simple joints just as fin plates, typical base plates, and like that. Well, that is all from my side. Back to you, Jakubus.
Thank you very much, Dominic. That was incredibly interesting. We just have a question in the chat. Johan Duplessis is asking, are friction grip bolts supported?
Friction grip bolts, does that mean preloaded bolts?
I imagine, basically. Yeah, I imagine preloaded bolts, yeah.
Yes, they are available in our software as well.
Awesome. Okay, Johan, I hope that answers your question. If not, you're welcome to remind us again. But I trust that answers the question. All right, brilliant. Thank you very much for that, Dominic. That was incredibly insightful. And just to all of our attendees, that all of the information is available on IDEA StatiCa's knowledge base as well. So you can actually go after the webinar, you can go to the website, and you can find a ton of technical information as well. And I think these sort of things, especially just with the confirmation of the verification and validation by universities around the world, that it gives us confidence as designers that we can really get the most out of this package and approach it with confidence. So, all right, our next section is moving on to concrete, and Andrej will be presenting this to us. We'll be looking at our concrete detail, and then I'll hand over to Andrej, and he can then take it from there. So go for it, Andrej. The floor is yours.
Well, good morning, everyone. Nice to be here with you. Can you please confirm you can hear me and see my screen?
Andrej, you'll just need to swap your display settings again, just like we discussed.
Thank you.
Okay, Epic,
now it's
thank you.
Okay.
Yeah, and I see attendees are saying that they can hear you, so go for it.
Well, I'd like to present to you our concrete application detail. As the name suggests, the main focus of this application is not on the whole global analysis of the whole structure, but only on some regions. But as you know, you got these B and D regions. In B regions, you can model them quite successfully only with one-dimensional elements. But in D regions, the same assumptions don't apply. These are regions with concentrated loads, change in geometry, openings, and so on. And these are usually analyzed separately using some other software or by hand using so-called strat method. This method is well described in literature and in codes, but it's got its limitation. Work with it, it's tiresome, and it can't provide serviceability limit states code checks. That was one of the reasons we developed the CSFM method, that's compatible stress field method. I don't want to go too deep into theory. I just say it's a finite element method where the concrete is modeled with shell elements and the reinforcement is modeled with one-dimensional rod elements, and they are bond together with concrete through multiple point constraints. The analysis is nonlinear because the tension, the concrete tension is completely neglected. And this method, here you can see what's the difference in results you get with strat method. There are discrete strats, discrete ties. What you get through CSFM is stress in each rebar and stress fields, continuous stress field in concrete. And we can, using this method, we can provide all required checks according both EN and American norm ACI. Those are ultimate limit states. You can check concrete strength, reinforcement strength, and even the anchorage of reinforcement. And for serviceability limit states, we can check stress in both concrete and reinforcement. We can check crack width and deflection. So that covers all checks that are required. And here you can see what are the typical use cases of this application. As I said, here you can see those are the typical D regions, like a corbel, depth end of a beam, maybe with an opening. But as the method itself, it's general, it can be used to for analysis of a whole structure, like a deep beam that you can see here, or maybe precast beam with openings. In these examples, you see concrete and reinforcement, but it's important to know that we can model even pre-stressing. It's all available. Here are some examples of, let's say, more advanced models that are used in bridge engineering. And here, how you can model a wall with large openings, asymmetrical. In these cases, it's quite hard to construct a strat and type model correctly and work with it. That's all my presentation. I would now like to show you how you work with the application itself. When you start the detail application, you can choose a template you will start from. You can have 2D model type or 3D, but 3D is now in beta. There is much work being done on it, but for today, let's stick the 2D model. There are prepared templates for walls, beams, frame joints, and even bridge diaphragms. You can start from scratch with a blank project, but for now, we'll start with a wall. You can set some basic parameters here, and I will leave them as they are and create a new project. When you're using the template, everything is set. This is a complete structure you can analyze. You can see here in the tree menu, you can define everything that's needed. It quite nicely leads you from the bottom to the top, from the top to the bottom. There are some general settings, and then you can see our main member wall defined as rectangular wall with its width, height, and thickness. We can have more than one member in one model, so I can add here a new wall if I want. It can have other dimensions. It doesn't have to be a rectangle. You can define a polygon or import a shape from the XF, so the possibilities are quite rich. I will delete this new wall now, and I will only slightly adjust the geometry of this wall to create a little asymmetry. You can see the reinforcement adjusted itself automatically, and the line support here moved too. I will move it back a little. So we have a wall, we have opening defined here. We got two line supports that simulate, for instance, a column standing here under the wall. We can define load cases. We have predefined two load cases, one for permanent load and one for variable load. There are line loads at the top and a small load from side. I will leave those as they are, only to show you can use point loads, surface loads, you can define self-weight. And we have three predefined combinations. C1 is for ULS, and we have two combinations for SLS code checks. That is a quasi-permanent combination for crack width check and characteristic for deflection check. Rebars, there are, as you can see, four predefined groups of rebars. When I switch off the display of rebars, I can see each one as it is defined. There are two rebars at the bottom. You can see that there are two when you switch to the 3D view. Well, and there are these wire fabrics that's the 3/4 with diameter 8 in distance of 150. That covers, when I switch it on again, you can see it covers the whole surface, and it gets trimmed by the opening automatically, so we don't have to care for this. There's a nice tool I would like to show you, that the topology optimization. That's not the analysis itself. What this tool does, it takes the volume of the materials that are in the model, and it places it in the most effective way, so that the model has maximum stiffness. It should be quite fast. I'm a little surprised it isn't faster, but basically it creates a kind of strut and tie model for you, where you can see how the load from the top line of of the wall finds its way to the supports. So here are the struts, here is the tie as you would expect, and here we can see a tie which is a little inclined thanks to the asymmetry that we input. But to make things a little more interesting, I would add two new openings. I can either create new or I can copy the existing one, and I will input their dimensions and position. So this one will be here, and the second one we'll place more to the corner. So now when we try to look for the topology optimization, it will be more interesting. I already did it on this model. I saved to save our time. You can see now it's more difficult for the load to find its way to the support. It has to go around these openings, and here in these regions we got ties. So this tool can help you to realize where you should put the reinforcement, where the concrete is under biggest loads. I already ran the analysis, which we do with this button, and you can see here we got many problems with in the construction. And if I look at the reason, it's where we would expect it. Here you can see that the reinforcement already yields, and that's the reason why the analysis wasn't completed, and it was because it was divergent. I will try to amend this situation by adding some additional reinforcement. You can see there's a possibility to simply add more additional reinforcement around the opening, and you can set it to whichever opening you like. We had problems around this one, so I added here, and the second problematic region was here under this opening. So I will add rebars here too. Those are straight lines defined aligned with this line edge number 1. We got 2 bars in each layer, and number of layers will be 5 in distance of 110. So now you can see we got this additional reinforcement, and we can try to analyze the construction again. I already did it to spare us time. So once again, I've switched the model. Here you can see this is the model with the additional reinforcement, and the analysis already complete. We got the green check marks for all the code checks, but we can study the results more thoroughly. We got summary results where we can see the stress flow in the construction structure itself. Then under this step strength, we can check the ultimate limit state. So here you can see the stresses in reinforcement. We can check the stress in concrete too. We can display percentage, the utilization of the concrete, or the direct value of the compression. We can check the anchorage length. Again, it's okay. And then there are the serviceability limit states where we can check compression in concrete for quasi-permanent combination, and there's another limit value for characteristic combination. Both are smaller than the limit value, so we are okay. We can check crack width too. The application will display all the crack width, and here we can see the extreme is here. It is compared to a limit value we can set here in the tab. And the last result I would like to show you are the deflections. We can display it as deformed, but this scale was probably a little too much. So we went through all the code checks that are required. You can see that it's quite easy to work with the application. The sample I chose is quite simple to make it quick, but you saw in the presentation it's possible to model much more complicated structures with this application. So that would be all from my side.
Thank you very much. Yeah, thank you,
questions?
Oh, yeah, let's if there are questions, please pop them in the chat and we will get to those. I see there from Pinar, does it accommodate wind loads or perpendicular loads for freestanding walls?
For this 2D application is only for loads that are in plane with the wall. What you are mentioning, that's a future with the 3D application.
Okay, awesome. So Pinar, yeah, not within the current module, but it is in the pipeline for the future. So thank you very much for that, Andrej. That was great and very interesting. I'm quite keen to jump into concrete detail soon. So, all right, on from concrete detail, we are now going to go into our live demonstration of steel connection. And so once you launch the steel connection application, this is what you'll find. So as before, even with detail, you see that there were some templates, and here it's the same thing. We've got different classes that you can run through, and this is of course just designing from scratch. You can see here the different geometries, and then also from there you actually get quite a lot of templates that you can work with. That's really very cool. So for this example, we'll just be looking at doing a haunch, and we'll choose that class over there, that particular geometry over there, and in the design we can actually see there's already a sort of a predefined haunch template set up for us. So I'll just call this our apex connection. Sorry, not haunch, apex, my apologies. It's an apex connection. We have our steel grade, we've got our bolt assembly, and of course these steel grades and these values can all be changed within the project file. So once you set these up, don't think that you are bound to them and you now have to create a project from scratch to actually change these values. And then in the design codes, you've got a lot of design codes. Of course, in the South African context, the Eurocode is by far the most applicable. So I'm going to keep these as is, and I'm going to click Create Project. So then it will actually set up the template for me with all of its imposed, or with all of its load effects and members. So these are just predefined load effects that we will definitely change. And you can see that these are operations. Now, operations are what you use to actually add or modify the connection outside of adding different members. So if I click on operation, you'll see that it says select manufacturing operation, and here we've got a ton of different manufacturing operations. So from gussets to connecting plates to shifted end plates to just end plates, etc. And then you can modify these operations from there on. So here you've got the plate-to-plate member splice. So, and you can actually see that operation there is a plate-to-plate member splice. Over here, you've got a cutoff plate and so forth. So this is what you will use to further modify your particular connection. So load effects, operations, and then members. So right, for this particular one, I'm going to start with my members, and I'm going to change their pitch. It's a 10-degree angle. Should actually be negative. So negative 10 degrees for both of them, and then negative 10 degrees. All right, this is so to simulate the slope of our rafters, and I want to change the cross section. So you can actually see the members are marked B1, B2, and you can actually turn those labels on and off. And the same for your plates as well. If you want to rename it, you can just simply right click, rename it, and it can be rafter 1, for instance. All right, this is B1 just for beam 1. All right, so I'm going to click over here. So we've got all of our different members to select from. And there is a massive list of sections to select from, which is really cool. We are interested in the universal beams, just the simple UBs. And then I'm going to change these to the 254 by 146 by 47 or 37. Apologies. So there we go. Select OK. You'll see that the member size will update, and I'll do exactly the same on the other side. So then my member sizes have been updated. And then we can proceed with just further modifying our model. All right, so we're quite happy with the size of these members. Now what I want to do is I want to modify these plates. So I'm going to change my plate thickness or the extent of that plate to 10 mil above. And then the bottom I'm going to extend. So 275, so it looks a bit wonky at the moment, but it will get better. So then we're going to select widen a 1, change its width to 250, and its depth to 500, and then do the same on the other side. Okay, so now we can't see the extent of this yet, but we can change that. So I'm just going to go to code setup, and you'll see here default length of standard member, so model and mesh, and I'm going to change this to 1.75. You can see there, it just changes what is displayed on screen. So let me just change that to, let's say, to 2. Let's see if that looks better. All right, and then we can actually see the full extent of the apex, all right, with the relevant dimensions. So you'll see as you go through the operations, it highlights the relevant values that you're looking at. You can actually match those values to what is within this palette over here. All right, so what I'm going to do next is just change the load effects. Now, all of your loads at a particular node are within equilibrium, of course, because we work with statics, right? And that's what you want. So you'll see here actually that it highlights if there are any unbalanced forces, and all the forces that work towards this node need to be in balance or in equilibrium. And you can actually use something like ProConsumer to get these type of forces once you've run your analysis within a larger model, and you can identify all the forces at that particular node, and you can actually import them or enter them in here, which is quite nice. So, okay, I'm going to enter in some values, and then we can actually just proceed from there. All right, you can see with all of those, all the forces are now balanced. So from here, it's quite simple. You can actually just start to calculate, and then we can actually run through the process. So I'm going to run my calculate. We might have a problem with the bolt spacing. It is possible. You can quite easily change that. But as we wait for this to finish, I'm really hoping that we don't have to change the spacing of the bolts. But if we do, it'll be nice and easy to do so. All right, we actually have a failure, which is cool in a sense, if you want to say it like that. And we can now proceed to our check tab. We can highlight our equivalent stresses. All right, you can actually see, you can see there that we're pretty much right on the limit of, we've just exceeded the limit of what this particular connection can handle. We can look at our mesh as well. We can actually turn our mesh on. That makes it quite nice when we look at our equivalent stresses. And we can also look at a deformed shape. All right, so you can see there's quite a lot happening here at this end. And we could just go back, and I'm going to change the member size slightly, just as a quick way of resolving this issue. Let's go to our UB again, and where it was a 37, let's go to a 305 by 102 by 25. Hoping that that will do the trick. All right. And let's run our calculation one more time. We'll quickly look at the reporting, and then we'll touch on just the checkbot functionality. I don't know if this is going to solve it, but I'm hoping that it does. You can see as it runs through the iterations, you see that load percentage increasing. And so it's just running through all of the different load effects and running through actually that complex CB-FIM that Dominic explained for. So that's all happening in the background now as we wait for this connection to be completely analyzed for us. Wow, and that actually did so much worse, probably because the flange is a lot thinner. So what was nice there, and to my surprise, I didn't think it would fail by that much, but we can see here that even increasing the size of the member, which is what I would do under normal circumstances, is I would just go and increase the size of the beam and check the whole process over by hand again. You can see it's actually, that was not the solution, right? So we probably need to look at just getting a beam with a much thicker flange and so forth, so that we can solve this problem. But very nice, actually working according to that plastic strain as well. The yield stress of the material is actually not the beginning and end of the material passing. I'm gonna sure that made such a horrible difference. But we can see here, yo man, this is a horrible connection. The apex is doing fine itself, but the rafters are failing, just failing terribly. And if we had a bit more time, I'd actually love to run through solving this issue quite quickly for us. I just want to quickly show us just the reporting as well. So you've got a lot of information here that you can actually create a report on. Once we click generate report. So if you were evaluating an existing connection, this would be very nice, right? But you can see you've actually got a full comprehensive report, and it's actually saying here in summary that, yo man, we've way exceeded that 5%. Oh my word, I'll totally lose my job if I needed to design that connection. But you can see here there's all of the summaries there, and there's just a lot of information in here. That's really very cool. And it's even giving you a bill of material, which is very nice as well. You can actually expand on this. You can see here with formulas. So if I click on that one there and we regenerate our report, you'll see that there should be a lot more information in here as well. Actually runs through all of the calculations for you, which is fantastic. I think these sort of reports are amazing, and if you're willing to put in the effort to actually read through them, I think you learn something, but they also just reassure you that the calculations are correct, and also how were those calculations performed, what were the variables. Now, it's very nice. I think if anybody's familiar with the Eurocode, I don't know if anybody can be familiar with the Eurocode, right? It's super hard to understand. I know that the 2023 version for Eurocode 2 has been released, And apparently the whole idea behind that is that it's easier to interpret, but you can actually see all of your variables here and the values for those variables are given as well, which is fantastic. So very, very simple as well. Very simple. And it is the same type of process, for your complicated connections. Is you'll spend a bit longer with defining additional members and defining additional operations. But that is the workflow in a nutshell. So just to conclude then with our checkbot. So we've got the BIM checkbot that is the integration between actually a lot of different software packages. This list has updated. This list is even longer now. And at the time we were, or IDEA StatiCa was integrating with over 22 software packages, and more packages will be included. We are very excited to know that Pro Consumo is in the pipeline as well. So I'm super excited to take that user friendliness of Pro Consumo and combine it with IDEA StatiCa. Yeah, I can't wait. I really can't wait for that integration to be available. And this streamlines the design process. So if you are just using it within a CAD package, so that would be something like Advanced Steel or Revit, it can actually take that geometry out of that space and into BIM checkbot. And in BIM checkbot, you can actually, it will identify connections, and you can then export those connections to IDEA StatiCa connection and design them over there. It doesn't update the geometry within the CAD model. So just so that you know, but it does allow you to actually take that geometry from the CAD model, and it uses that as a reference for steel connection. Of course, if you're using checkbot from within an FEA package, so in this case you'll see a robot listed there as an FEA package, it can actually import the loading for you as well, which is very cool. So that is really useful. The checkbot is amazing, and I would really encourage you guys to check out the checkbot as well. So right, with that, unfortunately, we had to conclude our demonstration on connection, just a bit faster than what I was expecting. But if you would like to see more, please be in touch with us as well. We would love to chat to you if you want a demonstration, if you actually want us to model a specific type of connection for you to show you how that would work within IDEA StatiCa connection, or you're interested in any of the other modules, please reach out to us at Micrographics. We'll be more than happy to schedule an hour-long demonstration or to answer any of your questions outside of the webinar as well. So if you don't know who to contact, you can just info at mgfx.co.za, or you can mail me directly, Jacobus with a C, right? JACOBUS at mgfx.co.za, and we can set up a demonstration for you. You just chat a bit more about the package. So just so that you know, if you have the package you're looking for support, you'll actually speak to us directly. And then, of course, if there's anything that we're unsure about, we'll actually chat to the amazing guys from IDEA StatiCa. And so just to say, as a last thing, as we just conclude with, if you have any final questions, you're more than welcome to ask. But just a massive thank you to both Dominic and Andrej for taking their time to sit in on this webinar with us. It was really incredible to have you guys with us, man. We appreciate all of your time all the way there from the Czech Republic. And yeah, we're just excited to work more with you guys and to pick your brains, man. So there's about a minute or so left if you have any questions. Otherwise, we will conclude with the webinar now, and then you can get in touch after the webinar if you'd like. So you're welcome to ask questions. Otherwise, this is the end of our webinar, and thank you so much for joining.
Thanks a lot as well from us, from the Czech Republic.
Yeah, thank you. It was great.
All right, I don't see any questions popping up in the chat. So with that, it is the end of our webinar. Please like and subscribe to our channel. There are other webinars coming up as well. And we thank you so much for joining in and for your time as well. Hope that you have a fantastic Tuesday and an epic week further, and we hope to be in touch very soon.